Welcome to today's lecture. This is our first online, and it is March 16th. And this is your organic chemistry class. I'm going to try to keep these lectures down to 20 minutes, so I've set a timer. Today we will review nucleophilic acyl substitution mechanism. You will need to know this mechanism for your quizam that you will have to download, and we'll trust the honor system. Will have to be uploaded on Thursday. When you send me an email, this is very important. If you do not do this correctly, I will not grade your problems. CHE314. And so if you're uploading your exam, you'll want to write quizam 3 and then put your name. I want first and last name. Okay, I have over 80 students that will be submitting assignments in all my 4 different classes. So I can't guarantee that I'll grade it if you do not do this. Okay, you also need to upload your take-home quiz. All right, if you want me to grade that take-home quiz, you put subject 314 and then take-home quiz and then your name. My goal is to have things graded and posted in your Canvas by Friday. So this is gonna, normally I do a day turnover. This will probably be more like a week turnover. The other thing that's due this week will be at the end of these 20-minute online videos, I will give you a problem or two. Okay, so at the end of the week, so you can just do this once a week, you do need to upload those problems, and then you'd want to do and send an email. The subject would be CHE314, and this would be your online POGL. Okay, and then put underscore and then your name, first and last name. That will be worth 5 points per week. Okay, and then of course when we go to the next POGL workshop workbooks, you can use those problems. But right now we don't have any problems for this week, except for the ones I'm going to give you today. So you will have to watch this 20-minute video. Okay, so we're going to review the nucleophilic aryl substitution mechanism that you'll have to do on your quizam. And we're also going to review the reactivity order. Okay, so we'll review that reactivity order. And then the third thing that I want to focus on is just kind of some other reactions that we might have overlooked. Most of these are going to deal with the nitrile group. So if you remember, the nitrile is the carbon triple bonded nitrogen with the lone pair. And you're going to see, we're going to look at dibow reduction. And that will be what we'll do today. So, and if you have questions, I want you to post them to the discussion board. So I'm going to have a discussion board for every day of the class. You post your questions, and then I can answer them so the whole class can participate. Remember, you still have online sapling homework to do, so you'll have to keep up with everything. All right. So let's first start with the mechanism of nucleophilic acyl substitution. Like I said, of course, this is review, but let's look at the reaction of going from, let's say, an ester. So we'll do this ester here. Okay, so here we have an ester. And we want to convert this to, let's do transesterification. Transesterification. Does anybody remember what that is? So we're going to go from an ethyl ester, and if you actually put this in like methanol, CH3OH, this can, an acid, H3O+. So if you have alcohol and acid, we're going to do a transesterification, and our product will be the methyl ester. And the reason why it can do this is because you have a lot more methanol than you do ethanol. All right, so let's just do that mechanism. Let's make the methanol red here. Okay, we'll make the acid yellow. And then the leaving group, we'll make it green on the ester, the starting material. Okay, and then we'll put plus ethanol. Okay, that mechanism then. Well, is this a weak or strong nucleophile? Methanol. So methanol is your nucleophile. Strong or weak? That's right. It is weak. Okay, so we have to first protonate the carbonyl. So we have our ester, and it will be protonated. That gives the oxygen a formal charge of positive. Now we have a stronger electrophile, and so our nucleophile, the methanol, can come and attack that carbonyl, and we're going to make what? That's right, the tetrahedral intermediate. All right, so less tetrahedral means how many things? 4. So I'm going to make sure this carbon has 4 things on it. Now notice the nucleophile still has the hydrogen on there, so that's going to be a formal charge of positive. And when you're actually doing the mechanism, you would want to regenerate your catalyst. See, we got the H3O plus, the acid catalyst. And what does catalyst mean? That's right, it's used and regenerated. And the other thing is, when you're actually saying you have a certain intermediate, it's kind of important to make it a neutral molecule. Okay, so to be technically correct, this would be your intermediate. And when we have that intermediate, we put it in brackets like that. So yeah, there's your tetrahedral intermediate. All right. Now what happens? Well, we have to protonate we got the acid, so now we have another molecule of acid, and we're going to protonate the leaving group. Now since we're going from the ethyl ester to the methyl ester, which of these alcohols are going to leave? Right, the ethyl is going to leave. So that is the one we're going to protonate. You know that O-ethyl is not a good leaving group, but once you protonate it, you have made it a good leaving group. Actually, you've made it a great leaving group. So now that gets protonated. And we can draw that mechanism here. These reaction arrows go here, generate that, make that water. And then you're going to reform your carbonyl. So you want to reform the carbonyl. So these lone pairs on the oxygen are going to come down to reform the carbonyl. And this is going to be your leaving group. And when you do that, you have formed your ethyl. Well, this will be your methyl ester. But you want to go ahead and deprotonate it. So you see your water over here needs to regenerate the catalytic acid. All right, so then your product becomes the unprotonated neutral methyl ester. And you can see Me or sometimes CH3. Okay, so that is the mechanism of nucleophilic acyl substitution. I also said we would review the order of reactivity. So I found a little chart that I thought was nice, so we'll just go with this chart here. All right, so we have an acid chloride. And an acid chloride can go to an acid anhydride, which is your second most reactive carboxylic acid derivative that there is. And we'll just make this maybe just a methyl group there. So this is an acid anhydride. Now your acid anhydride can also go to an ester. So this can go to an ester, depending on what you have. Like if you have methanol, then that would be OCH3. And also your acid chloride could go to this methyl ester. This is an ester. We have the acid anhydride here, and we also have an acid chloride. What else we have? We have an amide. Esters can go to an amide. So if we have something like NH3 ammonia, like this. Okay. Here is our ammonia, which makes an amide. Amide. And the nice thing is the acid chloride could also go to the amide if you have an ammonia nucleophile. And the acid anhydride can go to the amide. So I'm going to circle. This would be your leaving group, right? This is your leaving group. Here, your ester is your leaving group. Now, you can go from the carboxylic acid. It's harsh, but you can actually go from an amide to a carboxylic acid. So you could do like strong sodium hydroxide and heat. And then you can go to your carboxylic acid. Since this is base, they'll write that it's a carboxylate. But then you can protonate it with water and make a carboxylic acid. The carboxylic acid is at the bottom here. And acid chlorides can go to the carboxylic acid. Esters, just basically in base, sodium hydroxide. Sodium hydroxide is your nucleophile. Acid chlorides can also go to carboxylic acids. Now, if you wanted to go to the acid chloride, what's your reagent? Yeah, that's right, thionyl chloride. That is SOCl2. And I'd like to go over that mechanism just to show you. So that's what we'll do next. And then we'll do some other chemistry. So let's go from a carboxylic acid to an acid chloride. Right? Now, thionyl chloride looks like this. And what happens here, this is a strong nucleophile. So you don't need any acid, okay? And you're basically going to get this is your nucleophile. So actually, this is your electrophile, strong electrophile, okay? This is your electrophile. This is your nucleophile. What happens is these lone pairs will attack here. The electrons go up to the carbonyl, reform, and this becomes your leaving group. So what you've made here is what we call an activated ester. So and then what happened to this hydrogen? Well, you got the Cl hanging out, right? And it'll just deprotonate that. So your intermediate is this thionyl activated ester. Okay, and this is the sulfurs. Remember the tosylase and those are excellent. I'm not even going to say good. I'm going to say they're excellent leaving groups. And so the chloride then will come in, and this will be an excellent leaving group. And that is how you make an acid chloride. Okay? Not that you need to see that. I'm not going to ask that mechanism. I am going to ask the nucleophilic acyl substitution mechanism, but I think it's good for you to see that you're converting this carboxylic acid, which is just a dud, that OH is a bad leaving group, in order to turn it into a good leaving group. You just convert it, and so it's converted to an excellent leaving group here. So you're just changing the leaving groups, and that's how it affects your reactivities. Acid chlorides can go into acid anhydrides, esters, and amides. The next thing I wanted to talk to you about is, so we've done transesterification. Hold on for 2 seconds. The nitrile. So let's look at some nitrile chemistry, and then I'll give you Ural's problem. So a nitrile. How do you make a nitrile? Hold on for a second. Okay. Formation. Okay, so how do you make a nitrile? You can make a nitrile. We did show you this slide where you take an amide and you react it with phosgene, which looks like this, which is a dehydrating agent, which means it loses water. Okay, minus water, and that will make a nitrile. Okay, so you've lost this oxygen and those two hydrogens to make two new bonds, and there's your nitrile. So that's one way to make a nitrile. The other way is just SN2 chemistry, right? So if you have an O-tosyl group, so toluene, sulfonyl chloride, O-tosyl, it's an excellent leaving group, and you react this with a great nucleophile like sodium nitrile. Cyanide, probably heard of cyanide. Okay, so we got 1, 2, 3. This is an SN2, and now you have the carbon, new carbon here, of the nitrile. So that's another way. And then you know how to make aromatic ones. This was the Sandmeyer reaction. So if you have an aniline, and you react this with copper, oh, I'm sorry. First thing you have to do is sodium nitrite, that's NO2, not nitrate, which is 3. This is nitrite. Okay, and HCl, that makes that intermediate, the diazonium, which is a great leaving group, right? So this is the diazonium. Di means 2, azo means nitrogen, so diazonium salt. Nitrogen is an excellent leaving group. The atmosphere is 78% nitrogen. And then what happens, you can react this with copper cyanide. This is called the Sandmeyer reaction, anytime you use the copper on these. And that basically does just a replacement. Okay. All right, so we're reaching our 20-minute time. So I will just tell you this. Let's do the reactions of nitriles real quick. So when you have a nitrile, what can you do? You can react it with water and acid, and it goes through the amide, but then it will also go all the way to the carboxylic acid, and I think you know what to do with the carboxylic acid. You can also reduce these with lithium aluminum hydride and then with water, and that is going to make a primary amine. You could also react this with dibal, and I've been introducing dibal, diisobutyl aluminum hydride, diisobutyl aluminum hydride. Okay, so this is dibal. Usually you do about minus 78 degrees Celsius, and this will, whenever you see dibal, think of aldehyde, okay? Because you'll see that on the ACS exam, if we end up taking the ACS exam, right? So 1 dibal, and then you always treat this with water or acid. Either way, it's okay. It's an aluminum. You got to break up the aluminum oxygen. But there's your aldehyde. Okay. The other thing you can use dibal on, so just talking about dibal here, those other reactions I wanted to hit. If you go on acid chloride, so you can take an acid chloride and use dibal, and that will give you an aldehyde. You can take the nitrile, right? We just did that one. I think I threw in an extra carbon there, folks. Okay, and then the other one, an ester. So an ester will reduce with dibal to the aldehyde. Okay? Now, for your question, for your POGIL points, for your online POGIL points, I want you to fill in the missing boxes. So you're going to take, so this could be online PG question 1. You got the cyclohexene, and you add HBr. What is A? I'm going to give you C6H11Br, and then I'm going to give you the next reagent, magnesium, copper, or carbon dioxide, and water and acid. I mentioned this once. So what this does here is it will make a carboxylic acid. So I'm going to go ahead and give you that one because I've only mentioned it once and I didn't make you do a reaction sheet for it. Okay, so we need to fill in A. I gave you this one, and then when that carboxylic acid reacts with methanol and acid, what is B? I will give you CH314O2, and then you want to take that with lithium aluminum hydride and then water. Okay, and that's going to give you C. What is C? And that's C7H14O, and then you're going to react that with an acid chloride. So what is D? And that's going to be C9H16O2. And the other thing, so that's question 1. Question 2 is the, I want you to show the mechanism from the conversion of C to D. All right, I'll talk to you all later, folks.